Welcome back to our channel. Welcome back to this video. Today we are going to see a question on relations. If this is your first time on our channel, please do not forget to click on the subscription button and on the notification bell in order for you to get notified when we upload new videos. Okay, so let's get started with our problem. A relation R defined on the set of ordered pairs of the set of real numbers by xy is in relation with st if and only if x squared minus s squared is equal to y squared minus t squared. Show that R is an equivalent relation. To show that a relation is an equivalent relation, it is one, or an equivalent relation is one which is reflexive, symmetric, and transitive. Okay, so what do we have now? We have that the pair xy is in relation with st if only if x squared minus s squared is equal to y squared minus t squared. Now let's start by proving that it is reflexive. So let's verify reflexivity. Remember, x, y, s and t and r. So I can let my x, y, s, t, all of that to belong to the set of real numbers. Now, if r is reflexive, then for every point or for every couple which I will take, let's say for every AA, then since I have xy, yes, I'm going to use for every AA alone. For every AA which belongs in the set of real numbers, or let me use it without brackets, for any AA which belongs in R, then A should be in relation with A. Now, since we are dealing with ordered pairs, here we are going to verify that A is in relation with A. Now, what do we have? If we take point AA, is it in relation with the point A? Now, what do we have? It means this will be true if only if we have A squared minus A squared is equal to A squared minus A squared. So this is true if only if 0 is equal to 0. Now, since 0 is equal to 0, what does it imply? It means A is in relation with A, and hence this is reflexive. Now, the next property is symmetry. So let's go for symmetric. Now, for symmetric, what do we have? For every A, I'm going to use couples. For every AB, CD, yes, which belongs in the set of real numbers, if AB is in relation with CD, then CD should be in relation with AB. Now let's verify that. So we have our xy. Now in our case here, we are dealing with sy and st. We can still use our sy and st. Let's use sy and st. So I can say xy st. Let's use what is given. So you have xy st. st xy. Okay, so I'm doing this for us not to be lost. Now they have already given us, what do we know? We know that xy in relation with st means is true if and only if, what do we have? X squared minus s squared minus s squared is equal to y squared minus t squared. Now we are now supposed to show that S is in relation with ST is in relation with XY. So what does this imply? If I multiply all through by a negative sign, what do we have? It means we are going to have S square minus X square. This should be equal to T square minus Y square. From where ST is in relation with XY. Hence, R is symmetric. Now, if you are not seeing it, this is what I've done. I've simply used the laws of some basic principles of mathematics to come out with this. That's multiplying all this by a negative sign. But notice that if this then this, it means we have to leave from here and show this. Now what do you see here? If this is actually true and following the definition which was given to us, remember xy in relation with st means x square minus s square and y equal to y square minus t square. So if now it is the reverse, it means that we are going to have s square minus s square will be equal to t square minus y square, and that's exactly what we have here. And so it tells us that the relation is symmetric. Now let's go to transitivity. So we are going to take couples for every x, y, comma st, and I will take other 2 points AB, which belongs to my set R. If AB, that's if xy is in relation with st and st is in relation with AB, then xy should be in relation with AB. Now we are going to use the first two to prove the third. Now what do we have? Xy is in relation with st if only if we have x square minus s square is equal to y squared minus t squared. Now we take the next assumption, they said and. So if s and t is in relation with AB, so this is true if only if we have s square minus a square, s square minus a square will be equal to t square minus b square, t square minus b squared. I hope it's clear. Now what are we showing? Now we want to show that xy is in relation with AB. So what do we need? To show that xy is in relation with AB means we need something like x square minus a square is equal to y square minus b square. So what do? If I call this equation 1 and I call this equation 2, now let's do some maths. If we take equation 1 plus equation 2, what do we realize? This will mean that x squared will be left, negative s square plus s square we cancel, so I'll be left with x square minus a square. Here likewise y square will be left minus b squared, since negative t squared we cancel out with t squared. So what do we have? X squared minus a squared is equal to y squared minus b squared. Now have you seen the pattern? Yes. So this means xy is in relation with AB, hence R is transitive. Okay, now since R is reflexive, symmetric and transitive, then R is an equivalent relation. So this brings us to the end of this video. Thank you for watching. Please like, share and subscribe.